All right, well, welcome everyone. We are going to jump right in since we have a packed agenda today. My name is Katie Poss. I work for Turner Construction, and I am the co-chair of the CLF Nashville Hub alongside Nicole Ritter, who's an architect at Gresham Smith. I wanted to let everyone know that we are recording today's session and it will be posted to our YouTube later this week. The Carbon Leadership Forum of Washington at the University of Washington is accelerating the transformation of the building sector to radically reduce the embodied carbon in building materials and construction through collective action. They pioneer research, create resources, foster cross-collaboration, and incubate member-led initiatives to bring embodied carbon emissions of buildings down to zero. I encourage you to visit carbonleadershipforum.org to learn more, and also encourage you to join our Nashville Hub community on LinkedIn. Now I'd like to hand it over to the woman who taught me and hundreds of other students in MTSU's Concrete Industry Management program, including some on this panel today, not only about how fascinating and complex concrete is as a material, but also about the importance of addressing its environmental impact through innovation. And I'll hand it off to you, Dr. Heather Brown.
Thank you, Katie. Appreciate everybody being here today. And first and foremost, want to say thank you so much to all the speakers. I'm currently still a professor here at MTSU. So like Katie said, there's been a wonderful journey of teaching others about concrete. In about 45 days, I'll be transitioning out of academia and headed to the concrete industry and working with IMI Irving Materials. So excited about that journey, that next chapter. So the speakers that we chose today really embody, literally, no pun intended, but embody where concrete has already been making a difference, reducing embodied carbon, but where we can also look at some emerging technologies as well. Concrete is a complex material, and we're excited to showcase all of the options that architects and engineers have to truly be a part of the solution. So I'm going to speaker to give them a chance to transition into their slides. And we're going to start this program with Doug Rhodes. Doug Rhodes is a product development manager with Boral Resources. And today he will be talking about fly ash. Doug, you're on mute.
Sorry, I'd already started my stopwatch here too, so I got to regroup. Hey, thanks for the intro. I've broken my presentation down into 4 quick sections. Who's Boral? What is ash? How's it used? And what does it do to reduce carbon emissions? From the top, Boral Resources is the largest fly ash marketer in North America. We're in 45 states. We manage 100 different utility partners. Some of those are utilization, some of those are disposal. We offer a full range of CCP management. And when I say that, that's gypsum and other byproducts that the coal-fired power plants produce. As far as ash, if you don't know what ash is or how it's utilized, I'll be real brief in saying that there's 2 types of materials that come from the burning of coal in a coal-fired plant. One would be fly ash, and the other is bottom ash. As far as fly ash goes, there's 2 different types. There's a C and an F. An easy way to remember that is the C has a high calcium content. I came out of our lab in Taylorsville, Georgia. We are a CCR L ASHTO approved. Somebody's got some background there. I don't know if everybody's hearing me okay. We conduct all the QA/QC on the fly ash and any pozzolan sources we have in North America. Also, it houses our R&D department, which is in charge of looking at new sources, harvesting potentials, and beneficiation of marginal or unusable ashes by process or beneficiation. When we talk about the use of fly ash in concrete, typically it's between 10 and 15, maybe 25%, depending on the application and desired properties. If you don't know anything about fly ash, it provides a lot of durability attributes to the end product. in the arena of sulfate soundness, ASR reduction, or just decreased permeability if that's what you're looking for. Carbon emissions are reduced proportionately to the replacement of the Portland cement in the concrete. And I got a little bit of a description on the next slide. Well, you probably heard, well, there's no fly ash, or fly ash is running out. We can't get fly ash. Well, yeah, that's true. And in some regional areas, there are intermittent supplies. Boral is working on, we've been working for the last 5 to 10 years to secure harvesting sites, promote some natural pozzolan sources, and also working with beneficiation processes where we have a higher carbon content in ash, and we use a proprietary chemical called Restore Air to render that carbon inert and allow its use in concrete. And to the harvesting point, we've got 2 active harvest sites in North America that are working right now, and we're developing a natural pozzolan source in Arizona, and looking at several locations where that could be utilized. Yeah, thank you for whoever's clicking that slide for me. This is a sustainability report, kind of the brief or the big bullet points from our 2019. Our year goes June to June, so the next one will be out soon. In 2019, we sold 7 million tons, roughly 7 million tons of fly ash, and the replacement factor is generally 1-to-1 with cement. Sometimes it's a little bit of a different ratio, but typically it's in that arena. On that, if you're a concrete guy, the volumetric stuff comes into equation. On that basis, 1 ton of cement will kind of reduce, will reduce 1 ton of carbon emissions from the Portland cement replacement. So for every ton we can bring to market, we're replacing or avoiding about replacing it on a 1-to-1 basis. With Portland cement with fly ash, we can avoid 0.7 to 1 million tons of CO2 emitted. Again, our strategy is to increase the amount of pozzolans available to you, whether it's fly ash or natural pozzolans, to replace that Portland cement on a 1-to-1 basis or whatever the ratio is. There are challenges that surround that from a business standpoint. It's very capital intensive. If you're having to mill a material, like in a natural pozzolan scenario, the mills are quite expensive. The one that we're building, the facility we're building in Arizona, it's going to have a very high volume output. That's to be determined after a couple more studies, but it should supply a great deal of pozzolan over the next 25 to 30 year lifespan it's expected. So there are initiatives underway to have supplementary cementing materials in the arena of harvested materials, which are sometimes easy to get out of the ground and sometimes they're very difficult. It all depends on if they're commingled with bottom ash and have to be air classified to bring to market, or if they just have to be dried and screened. So our goal is to increase the amount of pozzolans that we sell year over, and our R&D department's working hand in glove with our sales staff to make sure that they can handle what we produce. And I think I've got about 30 seconds left, so that's kind of where I'm at.
Very good, Doug. Thank you. One comment, I think with everybody on the call, fly ash, one thing that a role that everybody here can play, because we all want to be end users of fly ash, is to put a little pressure on these private industry companies to consider being able to beneficiate their ash versus landfill, and working with companies like Doug's to put that technology in place. The technology exists, whole equipment exists to convert, let's say, bad ash to good ash, if you will. And it's companies like Boral that are out there looking for sources. It's easy for a private industry to build a landfill and just kind of do away with the problem immediately. So just wanted to comment there.
Thank you. Yeah, it's tough to dive into the weeds with 7 minutes.
Mm-hmm. Thank you so much, Doug. I appreciate it. Right, next, we have Heath Rogers. He's the market manager here in Tennessee for Lafarge Holcim.
Good morning. Thanks, Dr. Brown. As she said, I'm the market manager for Middle Tennessee. One of the products we market in the area is slag cement, and the product is made in South Chicago and brought to Nashville by barge to our terminals. I'd like to hit on a couple things. What is slag cement? Slag cement in concrete, and then how does it affect the environment? So main thing about slag cement is it is a byproduct of iron production. So it's the product that comes off the top during iron production. The product is then quenched and then ground to a fine powder. Slag cement can then be used in concrete to replace some of the Portland cement in the mixture. So when you look at Portland cement in a really small detail, basically whenever water hits it, it grows fingers, and that's how it gains strength. It grows this calcium silicate hydrate, and all that interlocks with the aggregate and the other cement around it. Slag cement has the same mechanism. It grows these calcium silicate hydrate fingers, and there's also some synergies with the Portland that is available. So you get a nice, dense, strong paste structure when using slag cement. So how's it used in concrete? The Slag Cement Association put out a chart basically showing how much in certain types of mixes that is typical usage. So the main thing I would like you to take away from this is slag cement is flexible. It's not a one-size-fits-all approach to different concrete mixes. It can be adjusted depending on the properties that you're seeking. So you can go with a smaller amount for concrete paving or a much higher amount for like mass concrete, depending on the properties that you're looking for. So how does slag cement help the environment, or how does it? So main thing would be you are able to reduce virgin material usage. You can divert an industrial waste byproduct from the waste stream and improve service life, which is that durability, strong paste matrix that we talked about. And then we can reduce the embodied energy and greenhouse gas emissions and lighten the color of concrete. So that light and color of concrete comes into play when you're looking at light design and also the heat island effect of concrete in the urban areas. So it's more reflective of the heat that is coming in. So let's look at a little bit closer on the reducing the embodied energy. Next slide, please. So as we talked about previously, Portland cement is an energy intensive product to make. As you can see, I'm showing the energy that it takes to make Portland cement versus the other two products, slag cement or fly ash. Portland cement is manufactured specifically for concrete production. The other two are byproducts that we're able to use in smaller amounts to help out the concrete mix. Next slide, please. So Slag Cement Association did some testing. They put together 4 concrete mixes and how much energy was used to make those concrete mixes, the total energy used. They looked at a 3,000 PSI, a 5,000 PSI, and a 7,000 PSI precast mix, and then a block mix. If you go to the next slide, you can see basically the savings of virgin material, energy, and carbon dioxide by replacing some of the Portland cement with a supplementary cementitious material. This chart is showing fly ash and slag, there are other things you can do, as we're going to talk about today. The main thing, if you would like to do a little bit more research, the Slag Cement Association has some great information on their website, slagcement.org. Two key places I'd like you to look is slag cement, the sustainability tab, next slide please, has a life cycle assessment calculator. It has LEED certification information and an environmental declaration, an EPD product information about slag. So that's somewhere good to go for some of the information we're talking about today. Second thing is the resources tab shows the slag cement information sheets. Next slide, please. Has 2 to 3 page documents about a lot of different information that relates to slag cement. So if you got a question about slag, how it would play into concrete, how it would interact with something, this is a great resource to start. You can also contact me if you have any questions. So thanks.
Thank you, Heath. That was wonderful on the resources. I appreciate the extra science insight too. Look at you talking about calcium silicate hydrate. Right, next we have Jay Witt. He is our technical service engineer for Lehigh Hanson, and he's going to talk about PLCs.
Thank you for this opportunity. And I'll see how we're working here. Good. Thank you for this opportunity to talk about Portland limestone cement and how cement manufacturers are making a conscious effort to lower footprint. My name is Jay Witt. I'm with Lehigh Cement. And when I first start talking about this subject, I always introduce the concept that this is not a new product. This product has been seen in Europe for well over 40 years. In Canada, they implemented it into their specifications in 2008, along with seeing some projects in the United States pop up in about 2005. One of the common questions we have for most people is how the DOT has accepted it. You can see from this picture, most of the DOTs are on board or they're looking to get on board with this concept. So I like to go through kind of a duration. We're implementing this into ACI specs in about 2010, but 2014, the DOT started to implement it into their process till we have the current day. Almost all of them are on board. If we look to our neighbors in the north in Canada, they haven't fully embraced this, such as we have one particular plant that's all they produce is a type 1L cement. And in the projects moving forward that are federally funded in Canada have to be implement type 1L. One other note here, the Army Corps has embraced it here just recently in May. And then in California, they are almost on board. And they have finished some research they've done. And in October, we expect to see that in their specifications. So really, what is PLC, Portland limestone cement? You may hear it that way, or you may hear it as a type 1L. It's a slightly modified version of our Portland cement. And what do I mean by slightly modified? Well, we're actually adding increased limestone percentage, about 5 to 10% in there. We're grinding it a little bit finer, but we're putting this into the process at the finish mills in the cement manufacturer. We're optimizing sulfate for set, and we're ready to go to look at the specifications. Where are you going to see these specifications at? 595 is the ASTM, ASTRO is 240. And where are the clinkers coming from? Well, we're using it from the same clinker we're using for type 1. Our main goal from a cement manufacturer is to have equivalent performance. And how do we do this? Oh, there's basically 3 mechanisms that we look towards. One is particle size. The other 2 are based upon chemistry and how the interaction happens at that micro level. From particle size, we look at that. It's real easy to get caught up into this, but limestone is a little bit easier to grind and allows us for greater distribution, which greatly helps with not only the finish from a physical point of view, but also from a chemistry point of view. From a chemistry point of view, we can get really into detail in this, but the carboilluminates are going to help with the hydration of that cement. What's it look like in strength-wise? Most people, when they refer to a particle, it's compressive strength. Well, we got very similar results, and we use this term like for like, and it's not just adequate to the compressive strength, but also seeing flexural strengths and all the durability testing, as far as shrinkage, ASR, and sulfate resistance, we are seeing a like-for-like performance. What kind of advantages does this type 1L give us? Well, the primary advantage is we're reducing our CO2. We are reducing that carbon footprint, typically up to 9 to 10%. But a practical side of me is, what are the ready mix guys looking at? How do they change this? We like this because it is simply, they're using the same material, the same equipment, the same batch programs, the same mix design. We may only see a slight change in our admixture dosage, but other than that, we are implementing a plug and play aspect on this. There's no new equipment needed for this. So the next concept we talk about is GWP. Well, how do we quantify that? What gets measured gets improved. Well, we have on a website called greenercement.com, we're able to kind of adjust and modify and see what our comparison. In this comparison off to the right is a 564 mix. We actually had saved 21 metric tons using the type 1L. Well, what does that really mean? And to me, you got to quantify it over several years. They quantified it over 2012 to 2018. We actually took 70,000 passenger vehicles off the road by using this product. You can also look at it from a little micro point of view down lower in the graph there. That graph, by simply just implementing a type 1L, we will save 9% on CO2 reduction. But also, if you implement either an SCM like slag or fly ash, we can reduce that down to even 39%. Where are we using this at? We, as being Lehigh, the projects that we have already implemented, we've got one dating back to 2010 where we have a terminal and a silos built. We have roads that have been in existence since 2010. There's one in Iowa and in Denver, Colorado area that we have seen this product already being implemented. From a concrete producer, what benefit does it have to us? The lower the global GWP. From a contractor's point of view, where does he see it? We're seeing the main comment we get from a contractor is, we like the finishability. So that's positive. They're not seeing any too much change. From a public perspective, obviously we have fewer CO2 emissions. So the number one question we get from an engineer and architect: how do I specify it? And I will commonly resort to this page from the PCA. The PCA has a greenercement.com, and to simply dial it back, it's just changing one line item. You're changing a type 1, which is from a C150, to a type 1L, which is a C595. Sounds too simple to be true, but it is true. How much do we believe in this product? We being Lehigh, and speaking from that perspective. We have started our new plant expansion in Mitchell, Indiana, a $70 million expansion. We are utilizing this product right now this year. Mass pours have already been done, excess of 3,500 to 4,000 yards of this, and we're using it in slip form applications. So we're pretty proud of this product. We could see this being implemented throughout the nation. What resources? I've already mentioned greenercement.com. That is an excellent resource provided by industry representation that you can resort there. Got some great little videos, some short videos, so you don't get too distracted, but some good resources there. Appreciate the time. We're excited to see how this looks like in the industry.
Thank you, Jay. One comment or question: can architects and engineers specify EcoSim in their greater Nashville projects today?
Oh, yes, absolutely. We have that product available. It is regionalized right now, so you have to check your particular region. I know here in the Midwest, which I'm located, Ohio, Indiana, Kentucky, Illinois, we have that product available.
Excellent.
Thank you.
All right, next, I've got Allison Palmer. Allison is the Market Development Manager for Carbon Cure Technologies. I'm sure many of you have been hearing about this company, and they've had a lot of effort out there, and Allison's going to share the latest update.
Hi, everyone. My name is Allison Palmer. I am the Midwest Market Development Manager for Carbon Cure Technologies. So today, just going to talk about what the technology is and some of the expected results you can get from using it on some of your projects. So with that, what is Carbon Cure? So we've developed a technology that introduces CO2 that is captured from large industrial emitters like fertilizer or ethanol plants, inject it into the concrete mix during mixing, just like any admixture. Once introduced into the mix, the CO2 chemically converts into a mineral and is permanently trapped in the concrete, even if the building is destroyed later on. So ultimately, this process improves the strength of the concrete, which allows us to optimize our mix designs and reduce the cement content of our mix by about 5 to 6%, the material with the highest carbon impact, without impacting any fresh or hardened properties. So I'm going to go into this process in a little bit more detail, but ultimately the message that I want to come across is it's the same concrete being delivered to your job site, but with a reduced carbon footprint. So the use of CO2 mineralized concrete is growing rapidly across North America. We are in almost 400 concrete plants, been poured in 10 million cubic yards of concrete, resulting in 100,000 tons of CO2 saved to date. I'd also like to note we are in compliance with ASTM C494 Type S. I really just wanted to highlight here that we've been used in a wide range of applications ranging from Canadian winters to Hawaiian summers, and all very successful projects. So to understand our process of CO2 mineralization, just need to do a 500-foot view of how cement is made. So we start by mining limestone, AKA calcium carbonate, from a quarry. Heat that up to about 2,600 degrees where that molecule will actually split in half. One half of that molecule is CO2, which is the waste byproduct. For every 1 ton of cement that is created, about 1 ton of CO2 is emitted. That's where we get 7% CO2 emissions globally here. So the other half of that molecule is calcium oxide, which is the critical binding material needed to make cement. So then cement is shipped off to our concrete partners that mix it with aggregates, water, admixtures, other SCMs to form our concrete. And now this is where CarbonCure comes in. So we deliver a precise dose of CO2 into the concrete mix during mixing, like I mentioned, just like any admixture. And once this happens, the CO2 enters the mix looking like a dry ice or a snow, warms up to room temperature, thus turning into a gas. And once this happens, it's like a magnetic attraction that occurs between the CO2 and the calcium from the cement. These two molecules want to bind together and return to their original state of calcium carbonate, AKA limestone. So all we're doing at the end of the day is creating nano-sized limestone particles. And these are the reactions that increase the overall strength of our mixes, which allows us to reduce that cement content, like I mentioned in the beginning. So diving into a little bit of a case study here, we have a 4,000 PSI mix that reaches 4,000 PSI at 28 days. So the gray bar is our control mix, typical concrete mix, sand, water, aggregate, cement, SCMs. The black bar is that same mix, but with a 5% reduction of cement. So as you would expect, when you take out the cement, you see that big drop in strength. The orange bar is the same mix, but with a 5% reduction of cement and CO2 added in. So it brought the strength back up to where it was at about 4,000 PSI at 28 days. And this is a really great example of an optimized mix. The QC team works closely with our technical services team to figure out how much cement they can take out of a particular mix while maintaining that same historical compressive strength. So like I mentioned, CO2 has a neutral impact on the fresh and hardened properties of the concrete. In fact, if we didn't tell you CO2 was being used, you would not be able to tell. It has the same set time, workability, pumpability, temperature, finishing, no impact on air content, can be used with any admixture, aggregate, cement, SCM. Hardened properties like freeze thaw, pH density, durability, and color are also unaffected. So just to reiterate, CO2 has a neutral impact because we're injecting about 1 pound of CO2 per every cubic yard of concrete, which is about 4,000 pounds of material. That 1 pound of CO2 just wouldn't have an impact on temperature. It'd be like throwing a handful of ice cubes into the back of a freight truck and expecting it to cool off. So how much CO2 can be saved? At the end of the day, this process reduces approximately 25 pounds per cubic yard, but that figure can vary quite a bit depending upon the mix design. So the first way we calculate this figure is through that 1 pound that I mentioned that is injected, chemically converted, or in other words, sequestered. But the majority of the carbon savings come from the ability to reduce the cement content. So when we're reducing cement by about 5 to 6%, we're reducing about 20 to 40 pounds of material. So those savings can really add up on any given project. If you're doing any sort of back of the napkin math, a safe figure to use would be 25 pounds per cubic yard. But we have a lot of information with our concrete partners. So we are able to provide a project carbon savings estimate if we have the estimate of cubic yards and mixed designs being used on the project. So we can get a really accurate figure. So just want to highlight a reference project here locally in Lebanon, Tennessee, 225,000 square foot warehouse facility where IMI was the supplier here. We saved 140,000 pounds of CO2 on this project from 8,200 cubic yards, which is the equivalent of about 100 acres of trees absorbing CO2 for a year. So as I said, these carbon savings can really add up on any given project. And I'd also like to note that no project is too small or too large. So how can you help reduce concrete's carbon impact? Communicate your commitment to embodied carbon reduction throughout the communication supply chain early and often. So much of the time, we all have the same goal to reduce carbon, the carbon footprint on our projects, and we're just not communicating how to do that. Design strengths for what you need, and use SCMs, low carbon cement, recycled aggregates when available. And Carbon Cure is not the catch-all solution here. We really want to advocate that you can layer our solution on top of other carbon reducing strategies. And we really welcome the opportunity to collaborate. Remove unnecessary prescriptive specs and move to a performance-based spec instead. And ideally specify and or at least approve the use of CO2 mineralized concrete. And with that, I will pass it back over. Thank you, everyone.
Thank you, Allison. That was great information. And I'd like to highlight that we will be featuring a few more of Carbon Cure examples locally in a September webinar. And that will be our phase 2 concrete webinar. And we're going to use one of our local suppliers, IMI, to showcase how they've used it and how the process went both from a fresh and hardened properties and then also the specification process. So thanks, Allison.
Thanks.
Next is David Dodier. He is with Master Builder Solution, and he is a technical development manager. Welcome, David.
Good morning. Welcome, everybody. Let me grab control. So this morning, I would like to talk to you about our Master Exceed product family. And this family, we have several products in this family, which will help lower the global warming potential of your concrete and has been successfully used in many projects from the East Coast across the US. What is Master Exceed? So Master Exceed is a crystalline nanoparticle. It is a synthesized calcium silicate hydrate particle. So it acts in a mechanical fashion versus some similar technologies that may act as a chemical reaction. So it acts through mechanical binding. Again, so the Master Exceed family, it helps reduce global warming potential on concrete, and they make a good pair. I will show you some examples later on. So Master Exceed, we have been able to successfully reduce carbon reduction between 5 and 40% in using Master Exceed by itself, or in certain situations with combination of other technologies and products in the market. Master Exceed will help improve strength from 3,000 PSI concrete up to 14,000. And Master Exceed products help improve concrete performance, allowing for the higher level replacement of SCMs. So I'd like to show you a couple of real world examples using Master Exceed product. So there's one here, and this goes back to Jay's presentation. This is actually, like I said, you can use Master Exceed product in combination with other technologies. This particular example is in combination with a PLC cement. So the combination of Master Exceed and a PLC cement, we're able to achieve an embodied carbon reduction of 27.6%. That's based off of a reference mix, and these calculations as far as how much carbon you can, these these examples can be, you have to choose your examples appropriately. So in this particular example, I did use a straight 564 cement mix, and which resulted in 217 less pounds of CO2. I'll give you an example of an ultra high performance concrete. And this example is the Winthrop Center in Boston, a 14,000 PSI mix design, where we reduced the embodied carbon in the concrete by 32%. And this was using Master Exceed in combination with some other technologies available in the market, resulting in 421 pounds less CO2 in versus the reference mix. And the reference mix in this example, this was taken out of the PCA design concrete properties, a table in there basically referencing some high strength mixes. And one more. So here's a JP Morgan Chase in New York City. This is the largest one, where we reduce embodied carbon concrete by 45.1% in 20,000 PSI concrete. And the total reduction is 648 pounds less CO2. This is also in combination with other technologies, including Master Exceed product. And that is what all I have. Thank you.
David, thanks so much. Just to let the audience know, Master Exceed is in the Middle Tennessee market now. You can reach out to some local suppliers, local producers, and they have that available. And there's lots of projects that we can highlight again in our September webinar to showcase some of those local savings. So thanks, David.
Thank you, Heather.
Next, I have Joel Thornton, and I mentioned earlier that we really look at concrete to have both current technology and emerging technology. And Joel really represents a bright future for concrete, and he's here with Aries Clean Technologies, and he's the business development manager.
Yeah, thanks, Heather, and how you doing, guys? I just requested. I think I've got the control now. All right, hey guys, I'm going to be talking a little bit of a different presentation for you guys today from the previous one. So the speaker earlier from Boral did a pretty good job of explaining fly ash and its uses, but what I'm here to kind of present is a technology that called gasification, which has two byproducts. One is, I think, called synthetic gas, and the other is biochar, or as we've trademarked it, biofly ash. And we're currently exploring the use of the biofly ash as a sustainable substitute for fly ash. So let me talk to you a little bit more about the company. So we are a roughly 10-year-old company based in Nashville, Tennessee. We hold patents on two different gasification technologies. One is called downdraft gasification and one is called fluidized bed gasification. Now, the two different technologies have kind of different applications depending on the feedstock. So downdraft is targeted more at a woody sort of biomass-based agricultural waste type feedstock. And then the fluidized bed gasification technology is more targeted towards things with a lot smaller particle size. So we have been mainly targeting biosolids. So if anyone's familiar with biosolids, it's, you know, the product from municipal wastewater treatment plants, and the disposal of that product is becoming more and more difficult. And so what we do is we take that material as a raw feedstock in our process. So I'll go through the process very quickly, and I know I've only got a few minutes, so I could talk about this all day, so I'm not going to go into too much detail, but effectively we receive biosolids. They're wet at this point. Wet means 25% moisture content, so we need to dry them before we gasify. So we send those wet biosolids to rotary drum dryers, dry them to 90% solids content. At that point, they're suitable for input to the gasification process. Now, the gasifier, I'll talk a little bit further about the process in a sec, but there is two main byproducts from gasification. As I said, one is syngas or synthetic gas, and the other is biochar or biofly ash, as we're kind of marketing it. Now, the syngas has heating value. It's not a lot, but it's kind of a tenth of the energy content of natural gas. But what we do is capture that, clean the particulate out, combust it, and then send that hot flue gas to a heat recovery system where we pull the thermal energy out and use the thermal energy to dry the incoming biosolids. So at that point, the system is a self-sustaining closed loop system, no natural gas or any fossil fuels during normal operations. And the only other byproduct, as I mentioned, is the biofly ash, which is where it kind of ties into this conversation, which I'll go into in a second. So what is gasification process? So gasification is, or fluidized bed gasification in particular, is a fully enclosed vessel, a bed of sand, just regular sand in the bottom of the gasifier. We blow air through the bed. At a certain point, we hit what's known as fluidization velocity. That then the sand then behaves like a fluid. We introduce some initial heat. We introduce the biosolids at that point, and then the reactions of the biosolids, it's effectively like a thermal decomposition process. So the biosolids start breaking down into their individual components, and they start reacting kind of with each other. And that's what forms this producer gas or syngas. And then what's left over is the ash in the feedstock, and the carbon resist. They kind of resist that thermal degradation during the process, and then we can extract that carbon and ash mixture, which is what forms our sort of biofly ash. So one thing to kind of note is that it might sound like an incinerator, and if anyone's familiar with incinerators, they're very difficult to permit, or states and other countries even are cracking down on incineration, and it's a big sort of scary word, but the gasification process has been deemed by the EPA as not incineration. So we went to them with our technology and got a ruling on whether we were as gasification versus incineration, and they ruled that we were not an incinerator. So that certainly helps us, permitting and going into these new states. So how does that tie into this conversation? So as I said, biochar is the byproduct of gasification. It's a mixture of carbon and ash, which resists the thermal degradation in the gasification process. So depending on the feedstock, so as I mentioned, woody-based biomass there's a much higher carbon content, much lower ash content. So you get a really high carbon biochar. That material we actually sell on Amazon as a soil amendment, but we have multiple other uses for that. Also, we currently have a supply agreement with a textiles manufacturer that they are using it in the manufacturing process of their textiles. And then that leads me kind of the fluidized bed gasification, or the biofly ash. This stuff has a much lower carbon content, sort of 5 to 10% carbon. The rest is ash. And we've been working with the National University of Singapore, or they've been doing tests on replacing fly ash with a mixture of similar to this with a small amount of carbon in it, and seeing good quality results in strength of concrete and the different sort of concrete parameters. I'm no expert in concrete by any means, but they've shared some of those results with us. So a little bit of history on this fluidized bed gasifier projects. There was one operating in Sanford, Florida about 10 years ago. That plant actually ran out of money and shut down, and Aries bought the intellectual property out of bankruptcy. And so what we're doing now, which is kind of leading to my next slide, is we're implementing that same technology up in New Jersey, and we have a project that's just about to complete construction here in the next month or two in Linden, New Jersey. We're going to be taking in 430 tons a day of biosolids, and the only output will be 22 tons per day of this biofly ash. Obviously, we don't have, since we don't have a commercial plant up and running yet, we don't actually have the material to perform all the tests on our specific biofly ash. But as I mentioned, once this plant gets up and running in the next month or two, we're going to be sending that material out for testing, and we have a letter of intent with a concrete company to use it as a substitute for fly ash once they complete the necessary testing on the material once we actually have it. So we're really excited about this plant getting online here in the next couple of months, and once we do, we hope to kind of get these labs tests done and sort of prove it out as a substitute for fly ash. So yeah, it's all hands on deck here at the moment, getting Linden finished. And once we do, hopefully we see some good results. And that's all I have.
Well, thank you so much for joining us today. It's exciting to think about a new source of materials. He's looking for good solutions, and it
Yep.
seems like a great process. Thank you so much.
All right.
Our last material presenter is Joe Keating, president and co-founder of Vitro Minerals. So excited to hear the update on glass.
Thank you. My name's Joe Keating, and we operate a glass pozzolan plant just down the road in Jackson, Tennessee. So we're actually in the Nashville region. Let's flip to the next slide, please. So recently, about a year ago, we finally promulgated a new ASTM standard C1866 that addresses itself to glass pozzolans. Now, by way of definition a little bit, a pozzolan is a glass that reacts with the lime generated when you add water to cement and forms additional calcium silicate hydrate. So therefore, whenever you add water to cement, about 20% of what you get is lime, and that lime does not contribute to any of the properties of the mix. So by adding a pozzolan, which has to be a glassy substance, you get additional calcium silicate hydrate and denser concrete. So fly ash and metakaolin and biochar would be examples of pozzolans. Slag is a little bit different because when you add water to slag by itself, it's cementitious, but it also undergoes the pozzolanic reactions. So all of those are great materials, and they're available in very large quantities. The issue with glass is that it is available widely across the United States, but not in concentrated quantities, and it takes quite a bit of beneficiation to clean it up and get it ready for concrete. As sold in concrete, it's about the size of concrete powder, 95% passing 325 mesh, and it's extremely pure. Let's look at the next slide. So the glass pozzolan standard acknowledges two types of glass. One of them is called soda lime glass, which is GS, and that includes plate or bottle glass. Plate glass comes from windows, mostly sourced from post-industrial sources. Bottle glass comes from municipalities. And the second type is type GE, and that's a glass powder that's made from fiberglass reinforcements. So both materials as used as a pozzolan are extremely pure, and they will react a lot like Class F fly ash in your formulation. Let's look at the next one. So when you look at the different chemistries of the pozzolans, the glass pozzolans, the type GS, have one unusual characteristic, and that is they have high alkali content. And this kind of prevents them from acting as mitigators of alkali silica reaction. However, the type GE glass has got a very low alkali content, and it's an excellent pozzolan, can be used exactly like Class F fly ash, except that it's white instead of dark in color. Let's look at the next slide. So in most properties, glass pozzolans act exactly like Class F fly ash. You can load them at 20 to 30% cement replacement. It is a 1-for-1 replacement of cement. So the embodied carbon of glass is a bit more than fly ash because we have to do somewhat more beneficiation, namely grinding it to convert it into the proper particle size. So let's look at the next slide. On our website, vitrominerals.com, we have this document which you can download. And this document has got all of the properties that you can expect from glass pozzolans as compared to the properties using other pozzolans. So in general, the reactivity is a bit faster than fly ash. You get a higher strength build than fly ash. In fact, our specification is 75% at 7 days and 85% at 7 days and 90% at 28 days. So we have a higher standard for the glass, and it can be substituted at 20 to 30% glass. And the chloride ion permeability is improved, the sulfate resistance is improved, and all the properties that you would expect from a good pozzolan come to the fore when you use glass pozzolans. And of course, using glass pozzolans is a lower quantity market availability than fly ash and slag. There's millions of tons of fly ash and slag available. Our plant down in Jackson, Tennessee is about a 20 to 30,000 ton per year plant. We have another plant in Indianapolis that's about 10,000 ton. And they built a new plant in New York, actually Connecticut, that's going to be about a 25 to 30,000 ton plant. So these are not large plants, but they do take care of a municipal waste problem, and they do close the loop on everyday products that consumers use. Let's look at the next slide. So we have an environmental product declaration that's also available on our website. But in general, these embodied carbon and the global warming potential is about equal to slag cement at the same loading. So if you load 25% pozzolan, glass pozzolan into your mix, you get about the same carbon savings as you would with slag. Fly ash, as noted in an earlier presentation, is a bit lower because fly ash doesn't have to be ground. You just kind of almost harvest it from the power plant where it occurs, maybe particle classify it, so it's a little bit better. So all of these products are great products and are very suitable for using in cement. And we are a local supplier. We have a lot of information on our website, bitumenminerals.com, so that you can tell exactly what sort of properties you're going to get. We're doing Facebook test pour in Gallatin within a couple of weeks. We just finished another Facebook test pour in Decatur, Alabama. These things went great. So the glass pozzolans are a great pozzolan, and the type GE glass pozzolans are probably the best pozzolan in the world. They're just not quite as widely available. The cost into Nashville is about $150 a ton or so, which is a bit more expensive than slag cement. Thank you.
Thank you so much, Joe. It's exciting to hear about the ASTM. I think that's really helping the market widely adopt this material. So appreciate your efforts. So I'd like to wrap up the webinar with our resident concrete expert here in Tennessee, the Executive Director of the Tennessee Concrete Association, Alan Spartman, to share some words of wisdom.
Thank you, Dr. Brown. Appreciate that. I'm coming to you from the road, so I'm in Knoxville, Tennessee today. We were just involved in a interesting project here in Knoxville using insulating concrete forms for energy efficient home of the future being built by a local nonprofit. So that's fun and exciting. I wanted to, first of all, thank everybody else that has presented today. Just excellent presentations, great, focused, ton of information. So thanks to everybody else who participated. And the thing I wanted to underline to kind of close out, there are lots of things we can do from a material specification using pozzolans or injected carbon dioxide, all these things that help and that we should take advantage of. But sometimes we just need to go back to the very basics and make sure that when we're specifying concrete, I think there's three things everybody should think about on your projects. And so one is, don't specify more than you need. And that has two dimensions to me. One is just the section or the thickness. So I know sometimes I'm reviewing plans and I'll see concrete sidewalks that are 6 inches thick. So as a ready mix producer, I kind of like that. That's more concrete for me to deliver, but is there a reason that you need 6 inches when 4 inches is the recommended thickness, even for light duty parking lots? So sometimes those things get stuck in our specs, and that's a third more concrete than you need for that example, which is a third more carbon footprint, regardless of whatever else you do. So just making sure that we're not specifying more than we need in terms of thickness or section is important. Very similar to that is what we're specifying in terms of strength. So are you specifying 5,000 when really all you need is 3,000 or 3,500. So that seems really basic, but to produce higher strengths, we have to put more cementitious materials in and more cement, and that drives our carbon footprint up. So making sure that we're absolutely specifying what we need and that we're being responsible, that we have a safety factor, that's important. But again, sometimes things just get entrenched in our specifications that are not necessary and that are driving our carbon footprint higher than it should be. And the final thing I would say, which is certainly related to the other two, is the timing of when you need your strength. So when we start to incorporate high percentages of pozzolanic materials and some of the other things that have been mentioned, one of the trade-offs for that is often slower strength development, or it can be. We don't always need our specified strength at 28 days. Oftentimes we don't really need it until 56 days or even much longer. And if we can take advantage of this higher long-term strength development that is a characteristic of most pozzolanic materials, that could actually make another substantial reduction in the mix designs on the front end. So I think you could sum all three of those points up with don't specify more than you need, whether it's section, strength, or timing of strength. Specifying appropriately can often result in significant lowering of our carbon footprints. I think I left a little time, Heather, so I'll flip it back to you. And again, thanks to everybody that's participated. Just truly outstanding information today.
Thank you, Alan. And if I may, I'm going to expand on your number 2 point, the strength. I'm in complete agreement, but in addition to that, what I'm seeing in specifications today is you might not actually specify too high of a strength, but you're also then specifying too low of a water cement ratio, which naturally is going to drive your strength up. So you may want a 4,000, but you may specify a 0.38, which naturally is going to produce somewhere in upwards of 5,500 to 6,000 PSI concrete at 28 to 56 days. So really watch those lowering of water cement ratios as well, because in that regard, you're actually increasing strength beyond what you need. And there's reasons to remove water from concrete, but it does have a detrimental effect on the overall, basically the embodied carbon. So thank you. All right, we do have time for questions. I appreciate all the speakers coming within time. You could come and teach some of my students how to give a 7-minute speech. So thanks so much. We've been taking some Q&A through chat. So I think Nicole and Katie have been monitoring that. Not sure that anything has come in, but we can open the floor for some open discussion.
Any questions? Okay. Well, thank you all so much for joining us. I know this was a jam-packed session with a lot of good information, but our goal was to give you just a picture of what's available on the market today. Oh, we have a question. When does the industry foresee PLC being widely available throughout the US? Jay, are you still on?
Yeah, I can answer that. It's pretty much very available throughout the Midwest and through the East. Through our companies, we've got it out available in the West. I would say that you're really going to be seeing more of this prevalent within the next year. As a cement perspective, we like what this product adds and the carbon footprint reduction. But we actually have it from a company point of view. Anywhere east of the Mississippi, we have it available.
I received a direct message. Can you provide contact info for all the presenters? Yes, we will send out contact information after this call so you can reach out directly with any follow-up questions.
right, Katie. We're probably, thank you so much, everybody. And I guess drinking from a fire hose doesn't make for much time to think about questions, but we'll send out that contact information and a recording link so you can share this presentation with others. And please join us in September for our case study webinar. We'll be sending out more details about that.
Thanks, everyone.
Joining.